start looking at chapter 13 since we finished chapter 12, which is integrals. Now, you have seen integrals before, but we will define integrals in a more systematic fashion and in a more proper way. So you know that, integrals are the opposite of derivatives, but how do we find them? Let's do it again if you have forgotten. So the question we would like to answer is find the area between bounded by the x-axis and some function f of x between a and b. X is equal to a, x is equal to b, and the graph of function f of x. The graph of function f of x. Right. So this is going to look like, this is my x is equal to a, x is equal to b, and maybe I have some graph which is something like this. This is my y equals f of x. Okay, great. So the area that I'm interested in is going to be this area, right? And this area. Well, now there is a small distinction. This area is positive area. Okay, and this area, which is below the x-axis, is negative area. Right, I want to separate these, and I want to find the total area bounded by all of these things. Well, how do I do this? Well, I'm going to say, consider what is called a partition. Definition. A partition P of the interval a comma b is a finite collection of points a is equal to x naught. So starting from x naught, which is going to be smaller than x1, smaller than dot dot dot, all the way over xn minus 1 is smaller than xn, which is equal to b. Okay, so I'm dividing my interval into n parts with n plus 1 points, and my partition is this set x0, x1, all the way up to xn, right? And so what am I doing with this partition? I want to look at the area of the graph in terms of the area heights at these points. So suppose this is my a, this is my b, okay, and my function goes something like this. So I'm going to draw x1, x2, x3, x4, x5, x6, x7, whatever, xn. A is equal to x naught, which is equal to a, x1, x2, x3, x4, x5, x6, x7, x8, and this is going to be b, which is equal to x9. So here I have partitioned this into 8 parts, right? 1, 2, 3, 4, 5, 6, 7, 8, 9 parts, my bad. 9 parts, of course. I'm starting from x0, right? So 9 parts. And I'm going to say, hey, all of these have the same length delta x, right? Great, all of these have the same length delta x, but counting the area here isn't helping me in any way. I have no idea what the area of these things is, right? What I'm going to do is I'm going to say, instead of going at whatever these weird things are, I am just going to look at the rectangles that these guys form. Okay. So it would be here, here. Maybe I should have colored this differently. Right? And I am going to say, hey, instead of the area of the entire function, let me look at the area of these columns, which I can find really easily, right? Because these are just delta x base. These are just columns of delta x as base, and height is f of xi, right? So height of this one is f of a, f of x1, f of x2, x3. Well, let me say dot dot dot, f of x6, f of x7, and so on, right? So I'm going to look at this sum, right? Now here I chose from the left hand side, right? I chose the endpoint of the left and I created the height using that. Instead, I could have done the exact same thing with the right hand side instead of the left hand side. So if my function would look something like this, oops. So 1, 2, 3, 4, 5, 6, 7, 8. Right? Then I could have looked at the heights from the right hand side and constructed columns from these instead of the left hand side, right? And that's going to give me a different estimate. And fair enough, I have no idea which one of these is a better estimate. It's going to be really hard to figure out which one is a better estimate. So this is my left hand estimate, left side estimate, left estimate, and this is my right estimate. Right estimate. And that's terrible. I have no good way of figuring out if my left estimate is bigger or right estimate is bigger, and so on. I would like some way of figuring out which estimate does better. And the trick is, great, if I just want to know if which of my estimates is more or less, or what information do I have, what I can do is I will say I am always going to look at the thing that gives me overestimate instead of underestimate. Okay, so in the first case, I'm going to look at the underestimate. So it's here. The smallest point is here, the smallest point is here, and the smallest point is here. Okay, so that's my underestimate. So this is an lower sum, and I can similarly, for the same, oops, for the same figure more or less, I can say, oh, now I'm going to look at the highest values everywhere, and I can be sure that what I'm now drawing is an overestimate, right? So this will be called an upper sum. Oops. Upper sum, right? I'm looking at the topmost point in the graph inside a column, and I'm making the height of that column to be that point. Here I was looking at the smallest column and looking at the height from that. Okay, so this is, if this height was m3, then the area of this a3 is equal to small m3 times, well, call me x0, x1, x2, x3, x3 minus x2, right? Similarly, x1, x0, x1, x2, x3, if this height all the way is m3, capital M3, then now this, the same a3, area of the third one, is now capital M3 times x2, x3 minus x2, right? So one of these is going to give the upper sum, and one of them is going to give the lower sum, right? So these are some values in that, right? M3 is lowest value of f of x in x2 to x3. M3 is the highest value of f of x in x2 to x3, right? This is how I'm constructing the upper and lower sums. So let me define some good way of writing these. I don't want to write this as, oh, this sum and this number f3, m3, how do I find this? Oh, look at this. Let me write a good way. Suppose that f is bounded on a to b, right? This is a closed interval. Any continuous function is going to be bounded, but this doesn't actually, the theorem does not say, oh, it has, like, not the theorem, the chapter doesn't say that, oh, I only consider continuous functions. So we just deal with a bounded function. Then let small m is equal to infimum, well, small mi is equal to infimum of f of x, such that xi minus 1 is smaller than x is smaller than xi, and capital Mi is equal to supremum of f of x, such that xi minus 1 is smaller than or equal to x smaller than or equal to xi, right? So then small m is the minimum in that interval, capital Mi is the maximum in that interval. Sorry. The lower sum of f over p, over a partition p, which will be written as L of f comma p, is then summation I is equal to 1 to m mi xi minus xi minus 1. And the upper sum of f over p will be denoted u of f comma p is similarly going to be capital Mi of xi to xi minus 1. Okay, well, clearly L of f comma p is f comma p smaller than or equal to u of f comma p, right? If I'm using the same partition, well, in each of these parts, small mi is smaller than capital Mi, and so this works out. Lemma, let P and Q be partitions of AB, and P a subset of Q. Well, then L of f comma p is smaller than or equal to L of f comma q, and u of f comma p smaller than or equal to u of f comma q. Whoops, this should be in the reverse order. U of f comma q is actually smaller than u of f comma p. So basically, if you make a finer partition, if you partition your set into even smaller intervals, your lower sum is going to become even lower, and your upper sum, no, sorry, your lower sum, wait, did I write it wrong? If P is P is a subset of Q. My bad. Okay, so P is a subset of Q means Q is a finer partition. So you're dividing it into more parts in Q. So if you're making a finer partition, your lower sum actually increases and your upper sum actually decreases. And it is it's actually quite easy to understand, right? Because if all my points in P are in Q, then the minimum on each interval x1 to x2 is going to be either the same or it's going to be bigger, right? Because let me draw a small picture here quickly. Let us look at originally an interval x2, x3, right? This is in P, right? And my graph does maybe something like this, right? So in that case, my green, which is my lower sum, would have height this, and let's say purple, which is my upper sum, as height this, right? So lower rectangle, upper rectangle. So the area that you have in the lower rectangle is the area of this small green, and the area and the value of the upper rectangle is the value of the purple rectangle. Right? Now suppose I have a finer partition, x3, x4, right? All these points are in the same place. Then now my lower rectangles look like, maybe I drew this slightly wrong. Actually, let me do this. Since my points don't need to be exactly in the middle, let me take that point x2, x3 here. It's just a finer partition. No one said that they have to be of the same height. Okay. Then my lower rectangles are these two. Right? And my upper rectangles are 1 and 2. Right? So for the upper rectangle, I am missing all this area, which I had in the previous case. And in my lower rectangle case, I have gained all this area, which I did not have in the previous case in Q, right? And so my value of the lower sum has increased while the value of the upper sum has decreased. So that's a figurative proof. Let's do a proper systematic proof. Consider a special case. Consider a special case. Special case in which Q has exactly one more point. Contains exactly one more point than P. So my P, which is, let's say, T0 to Tn, I throw in one point somewhere, which goes T0, Tk minus 1, U, Tk, and Tn. Okay. And so now I have A is equal to T0, which is smaller than strictly T1, smaller than ... smaller than Tk minus 1, smaller than U, smaller than Tk, smaller than ... smaller than Tn, which is equal to B. Right? Now let M is equal to infimum of M prime, let me call this M prime is equal to infimum of f of x, where Tk minus 1 is smaller than x, smaller than or equal to U. So, and M double prime is equal to infimum f of x, such that Tk minus 1, U is like on the other part. So U smaller than or equal to x smaller than Tk. So the interval Tk minus 1 Tk has been divided into two parts, right? And I get some interval, some new minimum infimums in there. Then L of f comma p is equal to summation I is equal to 1 to n small mi ti minus 1, right? And LFQ is equal to summation I is equal to 1 to Tk k minus 1 mi ti minus 1 plus on the interval M prime U minus Tk minus 1 plus M double prime Tk minus U plus summation I is equal to tk plus 1, sorry, I is equal to k plus 1 to n, what was I doing? N mi t, what do I get? ti minus 1, right? And therefore, to show LFP is smaller than or equal to LFQ, it suffices to show MK TK minus 1 is smaller than or equal to M prime U minus TK minus 1 plus M double prime TK minus 1 minus U. Right? Now, what is going to happen is, by definition of infimum, of tk comma tk minus 1, mk is smaller than or equal to m prime and mk is smaller than or equal to m double prime, right? Mk has to lie in one of the two. It could lie, like, the value can be in both of these, they could be equal, but if m double prime was smaller than mk, then that would be a problem, because m double prime would then be the infimum of tk to tk minus 1, right? And, well, therefore mk times tk minus 1 is smaller than or equal to, which is, well, technically exactly equal to mk times tk mk times u minus tk minus 1 plus mk times tk minus u is smaller than m prime u minus tk minus 1 plus m double prime tk minus u, right? Similarly, exactly same argument gives that, well, so therefore, let me say this. Therefore, LF comma P is smaller than or equal to LF comma Q. Similarly, exact same argument gives U F comma Q is actually smaller than U F comma P, because in that case I would be looking at the supremum, right? I'd be looking at the supremum of this interval, and if the supremum was, let's say, m prime, rather capital M prime, then that lies between tk and tk minus 1 also, right? So the supremum of u to tk minus 1 and tk minus 1 to u to tk minus 1 and u to tk has to be smaller than or equal to the supremum of tk to tk minus 1, right? And so I would get the other way around. Now for the, oops, that's done. And so for the final touch, I just say, well, if I have any random p greater than q, q containing p, well, for general p contained in q, well, strictly contained in q, create q, the partition q can be obtained from p, obtained from p by a sequence of partitions, p is equal to p1 is contained in p2, contained in contained in p whatever, let's say r, which is equal to q, right? Where each partition is just one extra element, where pi plus 1 minus pi, so set minus pi is one element, right? And then I would get that, oh, LF comma P is greater than, which is equal to LF comma P1 would be not greater, smaller than or equal to LF comma P2 is smaller than or equal to LF comma PR, which is equal to LF comma Q. And similarly, UF comma P, which is equal to UF comma P1 is greater than or equal to UF comma P2 is greater than or equal to UF comma PR, which is equal to UF comma Q. Right? And that does that for me. Then we get theorem 1. Theorem 1. Let P1 and P2 be two partitions. Let P1 and P2 be partitions of AB, and let F be a function, on AB, which is bounded on AB, which is bounded on AB, which is bounded on A to B. Okay, then, well, I can't compare if P1 and P2 don't exactly, one contains the other situation is not there, then I can't directly compare LFP and LFP2, but I can compare LF comma P1 is smaller than or equal to UF comma P2. Okay. Fun fact, it doesn't matter which one is P1, which one is P2, right? So the other way is also true. U of F comma P2, P1 is also bigger than LF comma P2. Okay. So proof, there is a partition P which contains both P1 and P2, which contains both P1 and P2, right? Namely, P is equal to P1 union P2, right? Well, we would not call it P because I don't want to confuse the U of union with the U of upper sum, so I'm calling it and giving it a name P. Then, according to the lemma, therefore, by lemma, I get L of f comma p1 is smaller than or equal to L of f comma p, which is smaller than or equal to u of f comma p, which is smaller than or equal to u of f comma p2. Ta-da! That's my theorem. Okay, that's my theorem 1, which is a great result, and that also tells me that corollary supremum over the set of all lower bounds, lower sums over any partition. P a partition P a partition of AB. Even if I take the supremum here, it is smaller than or equal to the infimum of all the upper bounds, the upper sums. P a partition A comma B. Okay. So this is a direct consequence in every single situation. If your elements of the bigger set are elements of UFP are bigger than LFP, we have seen this as a result that the supremum is bigger than infimum. Okay, exercise. This is a pretty easy exercise. Find UFP and LFP for all partitions, all P of 0 to 1 for f of x is equal to 0, x irrational, and 1 if x is rational. X rational. Okay. Now keep in mind every partition is finite. Okay. We are not dealing with infinite partitions. So here's a hint. What would happen if I take it to be small enough? Will it contain an irrational? Will it contain a rational? What would be the maximum in the set in that interval? What would be the minimum in that interval? Look at it. It's a really easy exercise. Okay. Then definition. The function f which needs to be bounded on a to b is integrable on AB on a comma b if the supremum of the partition, supremum of the lower sums of the partitions, P partition is actually exactly equal to the infimum of U f comma p a partition. So a function is integrable if the supremum is exactly equal to the infimum. Okay? And then the area from A to B, then the common value is called the integral of f on A to B, called the integral of f on a to b and is equal to, is denoted by integral from a to b of f. Okay, so this is called integral of f over a to b or on a to b, and we denote the value by integral from a to b of f. In case just some of you have forgotten, this symbol right here is the symbol of an integral. Okay, exercise. Is f integrable? Is f integrable on -1 to 1? And if so, show it is or it is not. Okay, first, f of x is equal to c, some constant c. Second, f of x is equal to 0, x irrational, and 1, x rational. So you did this example from 0 to 1, now it's -1 to 1. Does anything change? And 3, f of x is equal to 0, x smaller than 0, 1, x greater than or equal to 0. Okay, so I am going to show the answer to 3. I'm not going to do all of them. I'm just going to show you the answer to 3 because this will show you how to prove such a problem. If I had to show a function is integrable, it suffices to show there is a partition. Suffices to show a partition partition P such that f of L of f comma p is equal to u of f comma p, right? Because if these two are equal, then the supremum of this set of the lower bounds will be equal to the infimum of the upper bounds, because the infimum will have to be this particular number and the supremum of lower bounds, lower sums will have to be this particular number, right? So consider the partition okay, so this does not work, my bad. While it suffices to show, we won't be able to show this. Okay, so we will have to be slightly better about it because of my definition of integrability having the very specific condition that it has to be on the closed interval AB. And so my partitions will always have to have the middle interval 0 to 1 or 0 and 1 over n. So consider the partitions pi is equal to -1, -1 over n, 1 over n, and 1. Sorry, negative negative 1 over I, not n, negative 1 over I, and 1. Then m1 is equal to minimum infimum f of x from negative 1 smaller than or equal to x smaller than or equal to negative 1 over I, which is equal to 0, right? Capital M1 is equal to supremum f of x from negative 1 smaller than x smaller than or equal to negative 1 over I. Well, the function on this interval is constantly 0, so this is also equal to 0. Small m2 is the infimum of f of x on, now it is unfortunately a negative 1 over I to 1 over I. X smaller than or equal to 1 over I. So I could have technically done this in a slightly better way, but whatever. The infimum on this interval, since this has negative numbers, is 0. The supremum on this interval, negative 1 over I smaller than or equal to x smaller than 1 over I, the supremum is actually 1. Okay? And m3 is equal to infimum f of x from 1 over I smaller than or equal to x smaller than or equal to 1, which is 1 because the function is constantly 1, and capital M3 is infimum f of x from 1 over I smaller than or equal to x smaller than 1. Again, because it's constantly 1, it is 1. Therefore, L f comma pi is equal to zero plus 0 times the length of this is 1 minus 1 over I plus 0 times 2 over I plus what is this called? What is the third thing? 1 times 1 minus 1 over I. Okay, and the upper sum of this is equal to 0 times 1 minus 1 over I plus 1 times 2 over I plus 1 times 1 minus 1 over I. This is actually equal to 1 minus 1 over I, and this is equal to 1 plus 1 over I. Okay, and so therefore supremum of L f comma pi, p of partition is at least, well, all of these are partitions, right? These are not all the partitions that you could come up with. These are some of the partitions, so the supremum better be bigger than all of these, which is supremum, sorry, this should have been p of partition, not pi of partition. P is bigger than LFPI, where my PI are these above partitions, PI as above, right? Well, which is the supremum of 1I is in N, 1 minus 1 over I is in N, and you should know that this is equal to 1. You should be able to see, and you should know by your how supremums are calculated by now. You should know that this value is equal to 1. Similarly, infimum of u f comma p over all partitions p has to be smaller than or equal to infimum of these special types of partitions, right? If I'm looking at only special types of partitions, I'm looking at a subset, so this better be true, p as above. Well, that is exactly the infimum of 1 plus 1 over I is in n, which again, you should be able to confirm that that is 1, right? Therefore, supremum L f comma p dot 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 is equal to infimum u f comma p dot dot dot, and therefore f is integer. Okay, so this is how you show for 3, but sometimes you might be able to find just one partition where it just works out perfectly. Okay, then theorem, what is it called, 13.2, theorem 2. If f is bounded on a to b, then f is integrable on a to b if then f is integrable on a to b if and only if for every epsilon greater than 0 there exists a partition P of AB such that u of f comma p minus L of f comma p is smaller than epsilon. Proof? Well, this makes sense, right? The supremum should be the supremum of L's should be equal to the infimums of u, so you should be able to find something which is really close to the supremum in the on the lower sums, and something which is really close on the infimum on the upper sums, right? So let us show that. So if and only if is basically means a double implies. So we will first show that integrable implies there exists a partition. Okay, so actually let me just do this. Instead of if and only if, let me just write it this way. Okay, just so that my arrows make sense. Suppose there exists, for every epsilon greater than 0, there exists such a f, there exists such a p, right? With u of f comma p minus L of f comma p is smaller than epsilon. Well, therefore, since infimum of u of f comma p since infimum of u of blah blah infimum of the set u of f comma p is smaller than or equal p prime, let's say, over all partitions p prime is smaller than or equal to u of f comma p, and supremum over the lower sums f comma p prime over all partitions p prime, I'm not going to write that every single time, is greater than or equal to L of f comma p, it follows that the infimum of u of f comma p u f prime comma p f comma p prime, not f prime, f comma p prime minus supremum L of f comma p prime is smaller than or equal to epsilon, strictly smaller than epsilon, right? Since this is true for every epsilon, since this is true for every epsilon greater than 0, well, the only number smaller than every epsilon greater than 0 is a 0. Therefore, they have to be equal to 0. This infimum minus supremum has to be equal to 0, and therefore supremum L of f comma p prime is equal to infimum u of f comma p prime, right? And therefore f is integrable. F is so my bad, this arrow was reversed, I messed up. This arrow should be this way, not the other way around. I'm showing this first, my bad. I'm assuming the partition exists and I'm showing it is integrable. Well, that is that direction. Now suppose I'm looking at the other way around. Suppose now I assume that the function is integrable. Okay? If f is integrable, then the supremums are equal. Supremum L f comma p is equal to infimum u f comma p prime. F comma p prime. Not p prime, just p, whatever. Since I don't have such a partition right now. So now I can find, therefore, I can find partitions. Therefore, I can find partitions. Therefore, there exist partitions p prime, p double prime such that u of f comma p double prime minus L of f comma p prime is smaller than epsilon. Why? I can find a p double prime such that it differs from the infimum by epsilon over 2. That's right. By at most epsilon over 2. Similarly, I can find a p prime such that it differs from the supremum L f comma p prime differs from the supremum by almost epsilon over 2. If I have epsilon over 2, then the total thing is epsilon. Let P be a partition that contains both. Let P is equal to P1 union P2. Right? Then I get that uf comma p prime, uf comma p is smaller than or equal to uf comma p prime, p double prime, and l f comma p is actually greater than or equal to l f comma p prime. Therefore, u f comma p minus l f comma p is strictly smaller than or equal, well, not strictly smaller than or equal to, just smaller than or equal to f comma p double prime minus l f comma p prime, which is smaller than epsilon. Okay, so let me stop this video here and make another part for part 2.